Thank you all. I want to say I know you've been at the conference, so there's some exhaustion level setting in. I'm a little tired. My 15-year-old son and I decided to spend yesterday afternoon driving around the scenic parts of southwestern Oklahoma, not seeing tornadoes, but also not getting into the hail. So it was a reasonably successful day for us. One of the things that happens when people come to your place, you hope that they have a good experience and that things like the weather cooperates. And for those of you who've been here all week, softball-sized hail, tornadoes, man, it just doesn't get a whole lot better than that. So I will say this, that the largest hailstone that we saw sitting in a yard yesterday was, as we were driving back, was a couple inches in diameter, and it was sitting in the yard of a house that had one of those roofer signs on it. They were already repairing their roof from the storm 2 weeks ago, and I guess the guys are still on site so they can finish it up. Okay. I'm going to talk a little bit about forecasting in a changing climate, and really the change we're talking about here is really technological change, and some of the things that say maybe 5 to 10 years from now will become a part of operational practice that will hopefully help you all do your jobs better. And to start with, we want to spend a little bit of time talking about observations of rain in particular. Forecasting begins with observations. One of the things that at the Severe Storms Lab that we've been historically, I think, very good at is focusing on observations and what's happening and trying to interpret observations, especially in extreme events where one of the big challenges oftentimes is the observations you see are of really big things look a lot like bad observations. You don't believe necessarily this is what's actually happening, and so how do you interpret those observations? And then I'll talk a little bit about some of the new and experimental radars, particularly dual polarization radar, which is being implemented in the NEXRAD radar over the next couple of years, and then some examples of new radar technology, phased array, and then some of the multi-sensor analyses that have been going on at the laboratory. And then we'll talk about some of the new forecast models in just a little bit. Radar estimated rainfall. We've looked at storms with radars and used really simple examples to try or ways to estimate the rainfall. On the right side of this, you see traditional reflectivity-based estimates, and on the left is from the experimental dual polarization radar we have in Norman, and what will be being implemented nationally. And you can see that particularly in the southeast area, the reflectivity-based estimates provided a large overestimate of what the actual rainfall was because of hail contamination. If you would look at the precipitation estimates from last Sunday's storm, just based off of the reflectivity, they probably overestimate the amount of rain that fell by a factor of 2 in many places. That's in some sense the first and simplest thing that bringing the dual pol will do, bringing a whole lot more accurate observations of rainfall, particularly on the heavy end. And there are a lot of other improvements that I'll show you in just a couple of minutes. This is a study that was done we have a small basin out west of Oklahoma City, which is heavily instrumented. We have the complete basin has I believe it's 31 observation sites inside the basin, lots of streamflow measurements to where we can do a whole lot of hydrological testing, what's going on. And this is a series of different ways to estimate the rainfall from a series of events. The upper left is gauge, so that's somewhat of truth. And then the second one from the left on the top is based on the nonpolar metric. All the rest of them are different applications of polarimetric radars. And different ways we can try to do it as we've been experimenting over the last several years, different ways to do it. And one of the things that's important that I want to point out is that the least accurate in terms of RMS error is the nonpolarimetric radar. But it also turns out to have the smallest bias overall, to where in some sense it's better. And one of the big questions to ask, and then the most accurate is what's referred to as a synthetic rainfall estimate based off of the dual pol variables, but it has the worst bias. It has a severe underestimate overall on the bias. And so the question becomes, which is more important, and how do we try to put those things together? And well, one of the simple things you can do is to work on correcting the bias. And one of the big things the basin west of Oklahoma City allows us to do is allows us to use the streamflow measurements as an estimate, as a way to test how good the estimates of the rainfall are. It's a nice integrator. This is a plot of the streamflow estimate over a 24-hour period from what used to be called Tropical Storm Erin that came over Oklahoma City a couple of years ago and had over 7 inches of rain in 3 hours. It was a very interesting event to be living through. And this is a series of different ways to estimate. The nonpolar metric is the lowest of these plots. The observed are the plus signs, and based strictly off the gauge estimates is the black line. So it fits very well. But all of the polar metric estimates do better than the gauge estimate and provide a much better estimate of what was actually occurring. Actually, I'll click the button and get them on up there. And you can see now that using the polar metric variables, we actually were able to make a pretty good estimate of what the streamflow should be coming out of that, which implies that streamflow should be, or that the technique actually appears to be working fairly well, and it actually doubles the estimate of the streamflow. So even though that with the bias correction, we're able to do a very good job, and even though the reflectivity-based estimate is unbiased, it actually does a terrible job of estimating streamflow coming out of the basement. So if you're interested in what happens to water when it's on the ground, the nonpolar metric estimate sucks. And so this is one thing that hopefully will be available in the relatively near future that should improve hydrological modeling dramatically.